So this unit, unit 3, is called derivative rules. What do I mean by derivative rules? Well, we ended up last unit starting off with the focus of the rest of the semester, which is tangent slopes, instantaneous rate of change of functions. Okay? What's going on? How quickly is something changing at a specific point? And we developed this formula. This is the formula using a slope formula, just a simple slope formula, but it's the slope of any function at one single point. We created it by taking 2 points and putting them infinitely close together on any function at any x value. And we first discovered that these tangent slope graphs exist. Okay, and then we said, oh, we could find the equations of those graphs using this magic formula. Okay, cool. Well, I asked you to find the equation of the graph of the tangent slopes for this function or for this guy. Well, if you plugged that first guy into that limit formula, you would have to find this limit. You'd have to take x plus h to the 4th power. You'd have to do x plus h cubed, x plus h squared. This would take you probably the rest of this class period, okay, for this longer polynomial function. And if I asked you to algebraically simplify this, to figure out this limit, you would not know what to do. I wouldn't know what to do. Okay? So it turns out that this magic formula, which is very magical, is actually not very practical to use on a case-by-case basis. But it is very magical. Because what we can do with this, and what mathematicians did, is they used this formula right here to generate rules. So they said, oh, if I plug in a polynomial function, some like x to the n, what would happen? Okay? And they discovered something. And they said, if I plugged it in this type of function, what would happen? Okay? And it is from this formula that they generated rules, shortcuts, where we could bypass all of this and go straight to, and I'll show you why, the equation of the tangent slopes for this guy, just like this. Boom, done. How did I get that? I'll tell you how in a second, okay? But we will skip all of this stuff and learn the rule, which comes from the magic formula that enables you to go right from here to there, okay? And we will learn the rule for what is the tangent slope generator for sine. And these are rules that we will just have memorized. They come from our formula, but we're kind of done with the formula right now, okay? If you want to see how the formula was used to get these rules, please check it out online. Look it up. I'm not going to spend time proving the rules. I'm just going to tell you the rule, and you can take my word for it, or if you don't want to take my word for it, you can go online to find the proofs, okay? The first rule will deal with polynomial functions. So like x's, x squareds, x cubes, x to the 4th. Okay, and this first rule is called the power rule. And we can visually see the power rule in action. And you can have a visual understanding of what the power rule is by doing the following process. Let's go ahead and sketch the tangent slope functions, the equations of all the tangent slopes for these polynomial functions that are increasing in power. Okay, we have an x squared, an x cubed, and x to the 4th. Okay, I'll do the last one. I'll find k prime if this is k. So I see I have a 0 here, a 0 here, and a 0 here. I'll have a negative slope, a positive slope, a negative slope, a positive slope. So I got a negative to a 0. I have a positive before I get to the 0 at 0. I have a negative, I have another 0, and then I have a positive. So k prime the graph of all of the tangent slopes to k looks like this. Okay, you guys find h prime and g prime and f prime. All right, discuss with your neighbors what you notice. And I hear you guys saying the right things, okay? Each of these equations of the tangent slopes to the original function is a degree less than the previous function. If I have an x to the fourth polynomial function, its tangent slopes end up being some x to the third. Is it exactly x to the third? I don't know. I just know it looks like an x to the third. If I start out with some x to the third, I'll have some x squared. If I start out with some x squared, I end up with some mx plus b. If I have some mx plus b, what do I have? An x to the 0, which is just like a number, a constant, k. But you're right. The tangent slope graphs of polynomials are 1 degree less. Okay, so we can see that, man, a rule can be generated. We know that we have to at least take a degree away. But there's a little bit more to this rule. And it comes from, again, kind of when we were like distributing things for like x squared and I had x plus h squared, I had a 2xh in the middle. Okay, and then I factored out an h and I just had 2x, and 2x ended up being a part of my, f prime. If I had an x plus h cubed, my first term with just an h would be 3x squared h. And I'd factor out that h and I'd have a 3x squared. If I had an x plus h to the fourth, my first term with just h to the first power would end up being, and this is kind of using the binomial theorem and using kind of Pascal triangle, it'd be 4x cubed times h, and I'd factor out that h, okay? So it ends up not just being 1 degree less, it's a little bit more. And we'll come back to this before and now, and we'll come back to this notation heads up. Actually, no. Let's do the notation heads up right now, okay? Now, taking a derivative, what does that mean? This means finding the equation of a tangent slope generator. Okay? We start with some y equals f of x. The notation we will use will be a d over a dx. I use my d's like that because it's easy to write instead of d's like this, but you can see d's like this or d's like that. Doesn't matter. Just a little quicker for me to do that d like that. Okay? And you will say, hey, take that derivative, which means find the equation of f prime. Now, what is this notation? Well, yes, you're going to just right now notice it as take the derivative. This x means with respect to x. That x can change. All right? And what you will get, and maybe I should kind of move this guy over a little bit, is f prime. Okay, when I take the derivative of f, I get f prime. When I take the derivative of y, we can write that as y prime. Okay, y prime, f prime, same thing. But there's another notation that we can use for y prime. Okay, and this kind of goes with why we are using d over dx to find these equations of these tangent slopes. If you thought of this as like a fraction, and I multiplied the fraction by y, or y over 1, you'd have d times y, which is dy, and then you have dx times 1, which is dx. So what I'm saying is that equivalent to f prime, or an equivalent to y prime, is dy dx. So this is just a new way of saying, hey, my tangent slope generator equation equals this. But the reason why we use dx kind of shows up when you end up with this dy over dx. Okay? Because it turns out we're using this d for a reason. Okay, and it has to do with other d's that have been used in mathematics, like the Greek symbol delta. Now, in math, what does this delta, this triangle, mean? Change, like an overall change. Well, guess what this d is going to represent? Change. But not like an overall change over an interval. It will represent an instantaneous change. Now, if I asked you, what does delta y over delta x mean to you? What would you answer? Change in y over change in x, which then goes to slope, right? Now this is our, known formula for slope. What do you think dy over dx would represent? The instantaneous slope, right? Because instead of like an overall change of y over overall change in x, it's like the instantaneous change in y over the instantaneous change in x. So it's the instantaneous slope. Well, what's the slope at an instantaneous point? Tangent, a tangent slope. Exactly. So dy over dx, this is notation that you can think of and know, oh, that's just slope of a tangent. Okay? All of these are equivalent, though. You have to be familiar with, hey, find dy dx. You're like, oh, I'm just going to find the slopes of the tangents, the equation of f prime or the equation of y prime. They're all the same. Okay? We'll come back to this before and after. Let's move on to this first power rule. Now, we don't have an equation here, I just have an expression. So what we are doing is not really finding the equation of our tangent slopes, we are just using this rule for this expression. Okay? If I have x to the nth power, and I want to take the derivative of it, you are going to end up with something with 1 degree less. However, if you kind of use the limit formula and you start kind of distributing like x plus h to the 4th or x plus h cubed, you notice that after you factor out an h and cancel the h's, you'd end up with a coefficient of my first power. So it's almost like to find the tangent slope generator for x to the n, all I have to do is take the n and move it down first, and then subtract 1 from the power. In that order. So, if I ask you to find the tangent slope generator, to use this rule for x cubed, you'd take the 3, move it down, you'd have 3x, and then you'd subtract 1 from your power to give you 3x squared. Okay?
Is that how the question would look like on an assignment?
You'll see.
Okay.
We're just introducing it now, so we're just going to practice for a little bit. Okay. So before, if I said f of x is equal to x cubed, and I asked you to find f prime of x, the tangent slope equation for the graph of the tangent slopes to x cubed, you would say, okay, I got it. Hold on. Limit as h approaches 0 of x plus h cubed minus x cubed over h. You'd have to cube this, and you'd find it's like x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed over h. You would cancel the x cubes. You'd factor out an h. This h is gone. This comes h to the first. This turns into h squared. These h's would cancel. You would then plug 0 into h everywhere you see it, which would go here and here, removing those terms. What are you left with? Nope. 3x squared. Now, I say f of x is x cubed. F prime of x is, take the 3 down, subtract 1, 3x squared. Use your rules. It will save you a lot of time. Okay, but you see why it's the 3x squared? It's because when I distribute everything, I have all of these repeated terms, and I'd end up with 3x squared h's. Factor out an h, I have that 3x squared, which is left over. Okay, so that's where that coefficient comes from. Okay, now, quick practice. I'll do 2 of them, you do the other 2. I got x squared. I'd take the 2 down, and I'd subtract 1 from the 2, and I would get 2x to the first, which I'll just write as 2x. Let's look at the square roots. Well, a square root is the same as a fractional power. It's like x to the 1/2. So I could do the power rule with a square root. I could bring the 1/2 down and then subtract 1, giving me 1/2 x to the negative 1/2. Now, I will remind you of some exponent rules. If you go down here, we should remember that x to the negative n can be written as 1 over x to the positive n. We have done a couple problems with some negative exponents. So knowing that, I can go back and simplify this so that this is 1 over 2x to the positive 1/2. Or you have 1/2 times 1 over x to the positive 1/2. I probably would just combine those fractions to get 1 over x to the positive 1/2, or 1 over 2x to the positive 1/2, or 1 over 2 root x. So that's how you can use the power rule for a root and turn it into a fractional exponent. Go from there. Okay, you do x to the 7th and the cubed root of x. I guarantee you, many of you will mess up on the one on the right, the cubed root of x. Discuss with your neighbors what your answers are. You made the common error. It's your first time, though. It's what everybody does. This guy, easy. Bring the 7 down, 7x to the 6th. Okay? Why is this guy gonna be different? It's not. It's a third. So if I bring down the 1/3, I get 1/3 x. If I subtract 1 from 1/3, do I get negative a third? No. That's where everybody makes the mistake, because you're subtracting 1. So you subtract 1 from 1/2, you're subtracting 2/2. That's why you get negative a half. I'm subtracting 1 from 1/3, subtracting 3/3, giving me negative 2/3. Okay, so just make sure if you're working with fractions, we are working with common denominators and not just making things opposites. Okay? This is a lot quicker than multiplying by the conjugate, which is how we dealt with roots in the past. More rules that kind of come from the power rule. The derivative of a constant, the tangent slope generator of just some k, where k is a number. The derivative of x. So the derivative of x. Well, I should be able to get these graphically, and I'd prefer people to think about these situations graphically rather than go straight to the rule, because I want us to remember that it's all about tangent slopes. If I have y equals k, or if I have y equals x, you should be able to tell me, without using the limit formula, and actually without using the power rule right now, what our answers would be. Okay, discuss with your neighbors. What do you think the derivative of k is and the derivative of x? Okay, let me help you. What are the tangent slope values for this horizontal line, y equals k? 0. Are they 0 everywhere? Yep. Derivative of the constant is just 0. What are the tangent slope values for y equals x? I want a specific number here. 1, the slope of the line. Okay, that's one way, and I prefer you to think of things that way than using the power rule. But watch how the power rule can help us. If you wrote this as the derivative of kx to the 0, and you took the 0 down, and then you subtracted 1, you'd get k times 0 times x to the negative first. That would just be 0. Here, using the power rule, if you wrote this as x to the first, move that down, you subtract 1, what do you get? 1x to the 0, that's just 1. Okay? So, power rule works for that. Constant multiple rule is a great rule. It needs to be stated, but we'll find that it just naturally comes easily to us. Where if I'm taking the derivative of a constant times a function, I can just leave the constant and take the derivative of the function. How that will work with the power rule is if I have a constant times x to the n, I can just leave the constant. The derivative of x to the n is n times x to the n minus 1. And what we will find is that, oh, I can just multiply that k in the n times x to the n minus 1. Showing you a quick and easy example of that. You guys have space to the right. If I asked you to take the derivative of something like 3x to the 4th. Well, we can just go straight to this step and multiply the k and the n together and skip this. Which means take this 4, which is the n, multiply it by the 3, that's 12, then subtract 1, 12x cubed. Okay, it should come naturally to us just to multiply the original coefficient with like the new coefficient in our derivative. This helps us up here if I have, say, a k before the x. What is going to be the derivative of kx? K. It ends up just being the slope of my line. Okay, and it will work in the power rule as well. K times 1, x to 0. All right, so knowing these rules and the constant multiple rule, you can find the derivative of these 4. Now, all of a sudden I've just switched kind of the way that I'm presenting the problem. I first just said, do the operation. Now I have an equation of a function, an equation of a function, an equation of the function. And I'm asking you to find the derivative. That means I want you to find the equation of the tangent slope generator, the equation of the graph of the tangent slopes, which means you still will be doing the process, but you need to write it down. Get used to saying, okay, I'm going to take the derivative. Taking the derivative means I'm going to find the equation of the tangent slope generator, and you would take the derivative of y, and you'd say, oh, that's y prime. Or, using the notation dy dx, you can say dy dx, tangent slopes, are equal to. And then on the right side, you would use your power rule. You'd take the 7, multiply by the 4, subtract the 1, giving us 28 x to the 6. And it'd be 28 x to the 6 for both. So these are equivalent to each other. These are the same. You have to be familiar with it. So you take the derivative to find the equation of the tangent slope generator, the equation of the tangent slope graphs that we've been doing. Okay, do it for the other 2, please. Yeah. We want you to be comfortable getting rid of the negative exponents. Okay? All right. The next property that we need to remember, does anybody have any questions on what we're doing so far? This is new to everybody. I'm just going to take some practice. Nope. You can definitely write it as a 3 over root x. Okay, and you might have to, depending on the multiple choice question and the simplification required. So if you wrote it as 3 over root x, great. We will be dealing with fractional powers, like x to the 2/3. It's very important to understand that you can split this into a power to a power, like x squared cubed rooted. Okay? This is how we would write something using root notation. The cubed root of x squared. Now, usually if I give somebody the cubed root of x squared, they understand how to get the value. But if I ask somebody, what's 8 to the 2/3, they're like, I don't know how to do that. Okay? But remember what our goal is here and why we are finding these f prime equations, these functions. Okay? The goal is to find something that I can plug values into to find the slopes of the tangents to the original function. This function, this f prime, tells me how quickly f is changing. Okay? So I want to be able to plug stuff in. Well, we are going to end up with derivatives of fractional powers, and we may have to plug in a value and take it to a fractional power. So if I ask you what 8 to the 2/3 is, I would hope that you would know that it's equivalent to the cubed root of 8 squared. Now you know 1/3 is the same as the cubed root. So you think of what value times itself 3 times is equal to 8, and that's 2. And then 2 squared is 4. Okay, so that's probably not something every one of us remembers, but make sure you remember that for the future. Okay, and we're going to use both of these properties to find the next derivatives. So say we have like 1 over x squared. Our first instinct using the power rule is to say that the derivative of this, the equation of the tangent slopes, the equation of f prime, is just 1 over, bring the 2 down, minus 1, 2x to the first. But this is incorrect. The power rule only works when your powers are in a numerator. It does not work over division like that. So actually what I would do is before I took the derivative, I would simplify this. And I would rewrite this as f of x is equal to x to the negative second. Now it's important, if I add a 3 in front of that x squared, it does not turn into 3x to the negative second. That's wrong. Okay, it's just the x that is being squared that would be moved. You can either write this as x to the negative second over 3 or 1/3 x to the negative second. Then, now that we have our power in a numerator, we can use the power rule to get f prime equals, and this would be like 1 over 6x, which is wrong, but whatever, this is still wrong. Negative 2/3 x. Now here's where a lot of people make mistakes with the power rule. You're used to x squared going to 2x to the first. We're used to x cubed going to 3x squared. A lot of people say x to the negative second will go to negative 2x to the negative first. But no, you are subtracting 1 from the power. So this is negative 2 minus 1. That's the same as adding a negative 1. You actually go to the negative third power. Okay, so just make sure your arithmetic is solid. And if you'd like to simplify that to be negative 2 over 3x cubed, you may. Okay, so let's do these 4. I'm going to do the second one really quickly because this is different. All the other ones that we've done so far had x's. Well, this is a situation where we'd use a different variable to indicate I'm finding the tangent slopes. The variable I'm using is always my independent variable, and I wouldn't ddx this, I'd actually ddt this. Okay, I'm taking the derivative with respect to t because I have t's in here. It is notation. Does it matter tremendously right now? No. For you guys it doesn't. In the future it will. So when I do this, you can either say, okay, the derivative of g is g prime, or using this multiplication notation, you could say you have dg dt. Now this is for the changes in g over the changes in t. So if t is maybe an x-axis and maybe it's time, it says how quickly is g changing at a specific moment in time. We'll get into that more later. But for this guy, I would first rewrite this before I took the derivative of it as 4 over 5t to the negative second. Remember, the 5 stays down, the t squared moves up. Multiply 4/5 by negative 2, negative 8/5. Subtract 1 from negative 2, t to the negative third. Maybe here I'll write the simplified version. I get negative 8 over 5t cubed. Okay, you guys do the other 3. The remaining ones I would be ddxing, taking the derivative with respect to x. Okay, if you're struggling, you'll have to practice. This is brand new to everybody, but you'll need to be good to go for your quiz next class. Any questions about any of these 4 examples? Third one. Okay. I have 1 over 2 cubed root of x squared. Cubed root of x squared I know is x squared to the 1/3, which I know as x to the 2/3. So I actually think of this as 1 over 2 x to the 2/3. Now, I'm going to move this up so that it's x to the negative 2/3, but the 1/2 stays down. Do you need to move it up into the numerator? I like to keep it separate because maybe you don't realize, if you have x to the negative 2/3 over 2, that you'd have to multiply the negative 2/3 by that 1/2. So this is why I wrote it as 1/2 x to the negative 2/3 right here. Okay. Any other questions? The next one should come naturally to us as well, but it is important to state, and I'll just do it with a simple example. If I'm taking the derivative of some equation, some polynomial, that has multiple terms being added, or subtracted. Let me throw a minus in one of these. There's nothing special that goes on. You probably would naturally get to the same answer that I would get to. You would just take the derivative of all of the individual terms using the power rule, getting you 3x squared minus. Sometimes I don't like this minus because if this was, a negative exponent, it gets tricky. I like to change things to add the opposite. So I have plus, and then 2 times negative 2 is negative 4. This is just words of wisdom from a calculus teacher. Get rid of subtraction, change it to add the opposite. Plus 3x, the derivative of 3x is just 3. The derivative of the constant negative 4, what is that? Okay, we're new at this. We'll pick it up, okay? Seems obvious. However, if I were multiplying terms like this together, and I was taking the derivative of this, doesn't work out like that. This is not the same. You're not going to get y prime equals 3x squared plus 4x times 3 minus 0. Not right. Okay? So it's important to state this because it doesn't work. It's not the same for multiplication or division. Okay? Now, we've been focusing on this technique, this rule, but let's remember what these functions are, what they do, why we are finding these equations of the tangent slope graphs. It's because they provide an easy way for me to find how quickly the original function is changing or what the slope of the tangent is at any location. So here, notice the question that I'm asking. Find the instantaneous rate of change of the function at x or z equals 1. We first know that instantaneous rate of change is equivalent to the slope of the tangent. And we know that the slope of the tangent and instantaneous rate of change is the same as what's the derivative. So this is translated into any of those three. What is The slope of the tangent, what is the derivative at x equals 1? We can now quickly find the equation of the tangent slopes, the graph of the tangent slopes, and we can plug 1 into it. And we will find how quickly the original function is changing at 1. Let me show you really quickly. F. If I were to take the derivative to find the tangent slope generator, I'd get f prime is equal to, now I wrote this for this reason, negative x to the 4th over 2, just so that you know that you can rewrite it as negative 1/2 x to the 4th. When you use the power rule, 4 gets multiplied by the negative 1/2, you get negative 2x cubed. Then 3x cubed, 3 times 3, 9. 3 minus 1 squared. Derivative of negative 2x, just negative 2. The derivative of 4 is 0. Do you have to put the plus 0? No, but I'm going to continue to put the plus zeros while we're introducing things so that you know that the derivative of a constant is 0. Okay, great. What have I just quickly developed? The equation of the graph of all the tangents. You plug values into this. You get the slope of the tangent to the original function at any location that you choose. I want to figure out how quickly the function is changing at 1. I can plug in 1, and I get 5. Slope to the tangent to f at x equals 1. At x equals 1, the function is going up 5 units for every x unit. At that moment, it's increasing 5 y's per x. Okay? Now, you guys do this. How quickly is w changing when z equals 1? You are going to take the derivative with respect to z in this situation because z is the variable. Okay, go ahead and do that and find it at 1. Make a mistake? Oh. So I wrote w prime and dw dz, not because you have to do that, just because I want you to be comfortable with them being the same thing. And you could write either of these as w prime of 1 or dw dz at z equals 1. Which is 12 minus 2 plus 10, which is 20. Okay? That's how quickly the function is changing at that moment. Now, like I said, it does not work over multiplication or division. So if I have 2x plus 5 squared, and you were asked to take the derivative, well, your first instinct is possibly to write it as 2x plus 5 times 2x plus 5. But your next instinct might be to take the derivative right there and say, oh, 2 plus 0 times 2 plus 0. But this is incorrect. You're going to have to FOIL to simplify and then take the derivative. So let's go ahead and do that. FOIL, distribute everything. I like distribute everything. Okay, now, don't forget, all you've done is simplified. Make sure you find the derivative. All right, so we get 8x plus 20. That's simple. Plus 0, but again, you don't have to put the plus 0, but it's good for now to know that the derivative of 25 is 0. What about this guy? Now, my instincts are telling me to just take the derivative of all the terms, but that's not going to be right. So we're not going to do that. Instead, how can I simplify something like this so that I don't have a fraction and I don't have division? Any ideas? I could write it as 4x to the negative second, but I mean the 4 would stay down here. And I'd have x to the negative second like that. All right? I can do that, but I have multiplication now. So again, like I'd have to do something else so that I don't have multiplication or division. Other ideas? Could, but then I can only cancel 1x. I still have an x in the denominator. That's still division. If I have a plus b plus c divided by d, how can you rewrite this so that it's just something plus something else plus something else? A over D plus B over D plus C over D. That's what we're going to be doing. Okay, we just split up the common denominator. So I'm going to divide each term by the 4x squared. Now, let's see if you guys can do that. That's what you should get after you divide. X over 4, or 1/4 x, plus 1/2, plus 3 over 4x, or 3/4 times 1 over x. Now you take the derivative. You get 1/4 plus 0 plus, like this is 3/4 x to the negative first, negative 3/4 x to the negative second, or negative 3 over 4x squared. I'll tell you right now, you will see a quiz problem like this. Next class. And then the remaining problems, you'll see quiz problems up, like this guy. Let's start doing some applications, okay? So great, we now are kind of getting comfortable with this power rule, but what does that enable us to do? That enables us to find the equation of the tangent slopes of our original function quickly and easily. We had a test problem just like this. Yours was a little bit different, okay? This is from the previous year. And I said, find the equation of the line tangent of this function with x equals 2. Well, you would have to find f prime, right? And back in the day, which is like last class, you'd use the limit as h approaches 0 of f of x plus h minus f of x over h, and you'd find f prime. But now you say 4x plus 1. Is that the equation of the tangent line? Discuss with your neighbors. So equation of a line, right? 4x plus 1, that's the line, so that must be the equation of my tangent line. Discuss with your neighbors. Is that my answer? Don't forget what this is, what this is telling us. This is our equation for the tangent slopes to f. At any x. I want to find the tangent slope to f at 2. So you got to plug in 2. Discuss with your neighbors, what else do you need to do to find the equation of a tangent line? We got our parabola, we got our slope at 2 is 9, but I need that location where the tangent line touches my function. I need the point on the function. This is my slope, that's my m. My point comes from plugging in x into my original function to find this y coordinate. So that's 8 plus 2 minus 3, so that's 7. Giving me y minus 7 is equal to 9 times x minus 2. And that, my friends, is the equation of our tangent line. But now we can do other questions where, man, just finding f prime was daunting. But now finding f prime is the easy part of the question. So let's read this question. Find the x locations of a line or lines tangent, that's tangent, not tangent, to f of x equals x cubed minus 3x squared. They are parallel for the line y equals 9x minus 2. Why don't you guys take a minute to think about what you would do to find the answer to this? And why don't you discuss with your neighbors, because you're already doing it, what you think you should do to find this? So the key is that the slope of this line is 9, and we know that parallel lines have equal slopes, right? Okay, well, I got to figure out when does this have tangent slopes that are equal 9? Equal to 9. Well, I know I can find a tangent slope generator easily. 3x squared minus 6x now. Piece of cake. Well, I need to find the x locations when my tangent slopes equal 9. All right, solve this. It's been a while since we've had to solve equations. And boy, oh boy, if I had a nickel for every time I saw a student do this, I'd be a rich man. But, if I do that, anybody? Be honest. It's okay. All right, good. Even though you might be lying. If you're holding out on me, it's okay too. If I have a product equal to a number, that doesn't help me solve an equation, right? It's when products equals 0. That's what we want. So if you factored before you set your equation equal to 0, you do not help yourself out whatsoever. Please subtract the 9. Get everything equal to 0 when we're dealing with equations with x squareds and x's. Okay, this is a quadratic. Pretty much 100% of our quadratics we will see will be factorable. We will not have to use the quadratic formula, or we will not be able to graph to find the solutions. But if we do, you can use your calculator. So great. What do I do now? I probably want to factor out a greatest common factor. And then I can factor this nicely. And get the 2 x locations, the lines tangent to that are parallel to that. Okay, boom. The meat of the problem was like, what do we do after we found the derivatives? We will find many, many, many locations for the rest of this semester of locations of horizontal tangents. Discuss with your neighbor what you think you need to do here. What does it mean to be horizontal? Slope is 0. That's what it means to be horizontal. So we will take the derivative to find an equation for all of the tangent slopes to that parabola. We'll find for which x will our derivative be equal to 0. We set up an equation to solve, which we have not done much. Boom! We just found the location of the vertex to this parabola. Did I use negative b over 2a or anything like that? No, I used calculus. Do the same for the next one. This is a cubic. Maybe we have 2 locations, right? Cubic, up and down and up. Or maybe it's just like up and flattened out. I don't know. Let's find out. 3 times 1/3 is just 1. Fantastic. Ooh, here comes a tough one. Find k such that the line y equals 4x minus 9 is tangent to the function x squared minus kx. All right, so I got a situation here. I got a line 4x minus 9. And I have a parabola that can change. It's going to have kind of the same x squared, so it's going to open up the same way. But, like, can I shift a parabola so that I have multiple values for k, so that I have multiple different parabolas that end up tangent to this line? Okay? We feel me so far? Okay. What do these parabolas and this line, or what does one of the parabolas and the line share? Let's not worry about the second one. If I was a parabola that had y equals 4x minus 9 tangent to it, what would it share? What must be true? A point, right? A point. Very good. One of the points must be shared. That means for some x, the y's are the same. So that means for some x, the y's are the same. I got x's and k's. I can't solve that for k. Shoot, I need another equation. Here's the tricky part. What else do they share? Who said that? Schaefer, what do they share? It almost seems obvious because, like, isn't this a tangent line? But yeah, the slope of this line is equal to the slope of the tangent to the function at that location. Okay? So that is the other thing that they share, the shared slope. So the slope of this guy is 4. Well, the slope of this guy is determined by f prime. F prime gives me the slopes. Well, if I find f prime, I get 2x minus k, because k is a constant. Yikes, I got x and k in that one too. What should I do? Solve for k, substitute. We have a system of equations. We can use substitution to solve. I'm going to add the k, subtract by 4. K is equal to 2x minus 4. I'll then substitute it into my other guy. I get 4x minus 9 equals x squared minus 2x minus 4 times x. Make sure we distribute that negative, and let's solve. X squared minus 2x squared plus 4x. I got x squareds and x's. Let's go ahead and pull those x squareds together, same side combined. I can add the x squared, subtract the 4x. Isn't it nice how simple some problems are set up to solve? We can either factor this, or x squared equals 9, x equals plus or minus 3. All right, that's x. What is k? K is equal to 6 minus 4, which is 2, or k is equal to negative 6 minus 4, which is negative 10. Can't be, can it? Let's find out. y equals 4x minus 9. Y equals x squared minus 2x. And y equals, I'm going to go green, x squared plus 10x. Graph. Yes? Yeah? Looks like it. Zoom out. Yeah. Gosh. What's that?
What is it?
I entered the line.
Okay.
And then the two functions with the two different k's. Right? Just to see, like, did I find it? Yep. This line, those two green parabolas. Phenomenal. Okay. A similar situation comes from piecewise functions. And ensuring functions, especially piecewise functions, are differentiable everywhere. We talked about this in the fourth lesson. Differentiability means you're continuous. You can only have tangent slopes if you are continuous. You have points. And there's no sharp points. Well, you will see some questions where, hey, last unit I said find A and B such that F is continuous everywhere. I have changed the problem. I want the function to be differentiable everywhere. Well, two things. First thing, you got to be continuous. Just like last unit, to make sure the functions are continuous, you'd plug in 2 into little f1 and 2 into little f2. You set your equations equal to each other. Fantastic. I get 8a is equal to 4 plus b. The second situation is that we can't have any sharp points. How can I ensure that I don't have a sharp point? Sharp points occur if the slope from one side is different from the slope from the other side. Boom, sharp point. How can I make sure that the slope from one side is the same as the slope from the other side? Sure, but that's the continuity part. Check the slopes. I want to make sure that the slopes end up approaching the same value. How do I find the slopes of these two pieces? Take the derivative. Fantastic. So the slope of this guy will be determined by, now a is a constant, so 3 times a x to the second power. The slope of the bottom guy is what? 2x. I'm glad you said 2x and not 2x plus b. b is a constant, so the derivative of b is 0. Now, do these slopes need to be the same everywhere? No, because I'm using the top piece. The top piece is going to just like have the same slope, so whatever the slope is of the top piece. The bottom piece, whenever I'm using it for x is greater than 2, slopes are fine. It's just the slopes need to be the same when they meet up. That's at x equals 2 in this situation. So I actually plug in 2. I get 3a times 4, which is 12a, is equal to 4. It gives me a is equal to 1/3. Substitute in, find b. All right, go nuts. It's on the right. You can see it if I graph. I don't know how to graph piecewise functions on a calculator. I know there's some way to do it. I don't really care, honestly. But at least we can see right at -1 the smooth connection where they will meet up at -1 and they will have like the same slopes. In standard. I made a mistake. Oh, they meet up at 1. Sorry, not -1. So you can see, if I trace over it, that we got that line, and then it meets up nice and smoothly with that parabola. And that's the goal. We don't have a sharp point when that occurs. So this would be the graph of my piecewise function in green. Yep, just like that. Okay, moving on. We got 20 minutes. I think we might be able to cover everything. Let's talk about sine x and cosine x and its derivatives. Now, I talked about plugging in sine x into the limit as h approaches 0, like sine of x plus h minus sine of x over h. I don't know what to do there. So I'm going to just investigate. This is the graph of sine, just from -2 pi to 2 pi. Why don't we go ahead and sketch f prime? It's like we haven't done that for a trig function yet. Let's look at it. So I'm going to sketch it right on top of it instead of like what we were used to doing is creating another graph of f prime to the right of it. I'm just going to do it right on top of it in red. Now I'm going to tell you that right here, that slope, that's +1. And I'll tell you right here, this slope, it's -1. Whenever those are going to be the maximum and minimum slope values of sine. I'd like you to find all of them and plot them at all of the major extremes, at pi over 2, 3 pi over 2, 2 pi, -pi over 2, -pi, -3 pi over 2, and -2 pi. Let's go ahead and plot those values. So like at pi over 2, we have a slope of 0. 3 pi over 2, I have a slope of 0. It looks like at 2 pi, I have a slope of 1. Negative pi over 2, I have a slope of 0. Negative pi, I have a slope of negative 1. Negative 3 pi over 2, I have a slope of 0. Negative 2 pi, I have a slope of positive 1. Do you guys kind of plot those values as well? Well, connect them. Gosh, it looks like the same graph. What is the graph in red, Mr. Collioure? It's the cosine graph. The cosine of 0 is 1. The cosine of pi over 2 is 0. Cosine of pi is negative 1. F prime is cosine. The tangent slope generator to sine is cosine. This is where like math just starts to just go crazy and wild. You're like, what? So you're telling me values of cosine give me how quickly sine is changing? Yes. Magical mystery right there. Okay, well, if cosine is the tangent slope generator for sine, sine's got to be the tangent slope generator for cosine, right? Well, let's just check, just to be sure. Okay? So go ahead and do the same process. Let's confirm this answer of sine of x. That's the graph of sine. Is it the graph of the black graph from before? Nope. So that's wrong. But actually, if I just flip everything, it's right. How can I flip everything? Negative sine. These are two derivatives that you need to now know. That the tangent slope generator for sine is cosine. The tangent slope generator for cosine is negative sine. Okay? You won't have the luxury of doing this process in the future. Its tangent slope generator is negative sine if your function is sine. Its tangent slope generator is cosine. Okay? The negative is where people trip up. Okay? And if we want to just write it in this form, derivative of sine is cosine, and the derivative of cosine is negative sine. Great. Let's change this third one from r plus cosr to r minus cosr. And let's make that like negative 2 sine. Sines trip people up. So if the derivative of sine is positive cosine, the derivative of negative 2 sine would be negative 2 cosine. You just kept the 2, the negative 2. If you're taking the derivative of sine over 2, you can write it as 1/2 times sine. It's just 1/2 cosine. So here I would take the derivative with respect to r to get q prime or dq dr. Since I'm taking the derivative with respect to r, I'd think of this as being like an x, not like a constant. So this derivative would be 1. Now the derivative of cosine is negative sine. If I have minus cosine, it'd be like minus negative sine. This would turn into plus sine, r. Okay? It enables us to find equations of tangent lines. I don't have that written down. Thank you. Go. Sin x. 1/2 x minus pi over 3 over 2. And my friend sine, there's the tangent of pi over 3. Great. What else can we do with derivatives? Well, we didn't get to this on the 4th lesson, but we introduced it on the 3rd lesson, whereas motion and rates of change just go hand in hand. We talked about position. Where are you? We talked about velocity. Well, an average velocity is just our displacement over time. It's just the change in my position, the overall change, over the overall change in time. Right? It's the slope of position is an average velocity. What do you think the exact velocity would be? d of x of t over dt. The instantaneous change in my position over the instantaneous change in time. What is another notation for what we just kind of wrote? X prime. If you want to find exact values of velocity, take the derivatives of position. You don't believe me now, just wait. It's the same thing for acceleration. Average acceleration is the overall change in my velocity over the overall change in time. Guess what the exact acceleration is going to be? The instantaneous change in my velocity over the instantaneous change in time. What is that? The derivative of velocity. Again, don't believe me? Let me show you something. In physics, you're given a lot of equations. These are physics equations. And this, my friends, is the equation of a final position. You're given an initial position, that's a number. You're given an initial velocity times the variable time. Plus, you're given 1/2 a constant acceleration, which is a number, times t squared. Okay? And that was our equation for position. And then they gave you another equation for velocity. Okay? Separate equation. Seemingly unrelated. But, my friends, take the derivative of that position function. X prime of t. Now, let's see. X naught, the number. What's the derivative of the number? 0. So, okay, that's 0. V naught t, the number times t. What's the derivative of a number times t? The number. The number here is V naught. Then, 1/2 a number t squared. Take that 2, multiply it by the 1/2, subtract the 1. You're just left with the a and the t. Oh, it's that guy right there. Seemingly came out the instantaneous rate of change of position. Okay? So, when you took physics, this is why when you take calculus, this is why sometimes you're like, I wish I took calculus before I took physics. Because a lot of stuff starts making sense when you start talking more and more about rates of change. Given a situation like this, the free-falling position function of a diver who jumps off a 50-meter platform with an initial upward velocity of 3 meters per second is this. X of t's in meters, t's in seconds. What's the velocity after 1 second? You don't need to plug in the information into your velocity formula. You can create your own velocity formula by finding the derivative of position. The derivative of position gives you a velocity formula. You don't have to plug in things into equations. You're given one equation, you can find the rest of them from that first one. What's the acceleration? Well, hopefully it's gravity. Let's see. And it probably shouldn't be meters per second. I think it's probably feet. Do you guys have feet? Yeah, but isn't acceleration negative 9.8? Right. So when I find my acceleration, which is the derivative of velocity, and I get negative 32, probably means it's in feet per second. Okay? Velocity would be feet per second. This would be feet per second squared. Why is it constant? Gravity. We did it. 1 hour and 37 minutes. Thank you. I love